I have three examples of integrals that all three are of some sort of form of a sine. But what you're going to notice is that none of them are a basic type of sine. Okay? So I want to ensure that you are okay being able to evaluate these sorts of integrals that aren't basic by using a substitution. Now, quite obviously, the last one looks like it's the most difficult one, just because there's more terms and factors going on with it. Not necessarily the case. Whenever you're dealing with a composite sort of integral, what I always suggest is that the first thing that you might do is at least just try making the composition part the substitution. So let's go ahead for this one and at least try to let u be equal to what's inside of here. In other words, 2 pi x plus 1. Now, we're hoping that when we take the derivative, this is going to become u. We're hoping that the rest can be substituted as just dx, okay? And we might have to manipulate what we get for the derivative just a little bit so that way we can get to the dx. Let's take the derivative of this thing. Okay? So the derivative of u is just du. The derivative of 2 pi x, well, the derivative of x is just 1, so the x just goes away when we take the derivative, so we're left with 2 pi. And then because we differentiated with respect to x, it's 2 pi dx. The 1 goes away because the derivative of a constant is always 0. Now, there's good news and bad news. The good news is that we got rid of the x, which means that there's no more dependent variables. Unfortunately, the 2 pi is kind of getting in the way of the dx. So let's do this. Let's get rid of the 2 pi by dividing both sides of the differential by 2 pi. When we do that, du divided by 2 pi is going to be equal to just dx. And that's good news, because now we can substitute for dx back in the original integrand and then hopefully get to some sort of answer with this. So by substitution, our new integral solely in terms of u, we said that instead of sine 2 pi x plus 1, that's going to become sine of u. Instead of dx, we're going to substitute du over 2. So we get du over 2 pi, excuse me. Okay. Notice that 2 pi in the denominator is a constant. We have a rule with integrals that we can factor a constant out. One of the most common errors I see is that students will do this. They'll write a 2 pi on the outside, and they'll say sine u du. Think to yourself, what's wrong with this? Well, we started with a fraction. It was in the denominator. When we factor it out, it shouldn't be just a regular term that doesn't have a fraction. So what we're going to do is we're going to make this 1 over 2 pi. Okay? So remember, if it starts in the denominator, when you factor it out, unless it has a negative exponent, it should end up in the denominator. We know the antiderivative of sine is going to be negative cosine. So by our fundamental theorem of calculus, we get opposite 1 over 2 pi. Like we said, antiderivative of sine is cosine of u. Because it's an indefinite integral, we have to have the plus c. And then finally, just like any other problem with a substitution, we have to back substitute. So for our final answer, we're going to back substitute for u. And what I'm going to do is I'm going to move the cosine into the numerator, just to make it into one compact sort of term. So for a final answer for this, we could write this as the cosine of 2 pi x plus 1, which was our original u, divided by 2 pi. And I know that there's some of you guys screaming out there that are watching this that I forgot something. For those of you guys that can't see what I forgot, remember, there was a negative sign that we started with. So let's just bring the negative over here, and that's going to be our answer. If you don't trust the answer, of course you can always take the derivative of that. Okay? If you were to take a derivative, that would be a chain rule problem. Let's take a look at our second one. You would suspect that it's going to be very similar to the one that we just worked on, and in fact your suspicion's correct. You would start by making the internal composition be equal to U. So in this problem, I'm going to start by saying let's let U be equal to pi x over 2 plus 1. Just like the last problem, when we take the derivative, the x goes away and the 1 goes away. So our du is going to be just pi over 2 dx. Now, just like the last problem, we wanted to get to just dx, and it's the same thing for this one. Okay? So to get rid of a pi over 2, we could divide both sides by pi over 2. But what might be a little bit easier to do it in one step, rather than having to multiply by the reciprocal at the end, is just to go ahead and multiply both sides by 2 over pi. Now, notice what that does, is that it cancels out the pi's and it cancels out the 2's, so we're just left with dx. So if you have a fraction in front of a dx, the easiest way to get rid of that is to multiply by the reciprocal. So it looks like that 2 over pi du is going to be equal to our dx. Now we can substitute. When I substitute, instead of pi x over 2 plus 1, that's our u. Okay? Remember, every time you perform your substitution, whatever's in the inside is a good place to at least start. So I'm going to get sine of u. And then instead of dx, remember that dx is 2 over pi du. So I'm going to write this as 2 over pi d. In the previous problem, notice that what we did was we factored out the 1 over 2 pi. And that's exactly what we're going to do. We're going to factor out this constant 2 over pi. So we have our 2 over pi integral sine u du. At this point, we just have to take the antiderivative of the sine function, and just like in the previous, it's a negative cosine. So I get opposite 2 over pi cosine of u plus the constant of integration c. And then the last thing that we would do is we would just go ahead and back substitute for u. So if I go ahead and back substitute, I have opposite 2 cosine of pi x over 2, and I'm going to divide all of that by the pi. And of course we have to remember our plus c. I think I just noticed in my previous problem I forgot to carry over that plus c. So hopefully you weren't too angry with me for forgetting that. There we go. So what we can see is that essentially when we take the antiderivative, when we're using U-substitution, we basically end up dividing by whatever's in front of the x in some cases. And that's not always the case. So let's take a look at this last guy right here. Okay? Now obviously he looks a little more formidable, okay? Because there's more than just one x in the problem. But that doesn't necessarily mean that it's going to be any more difficult. Okay? So let's go ahead and see what we can do with this. Now you're probably guessing that the best thing to do is start by substituting what's inside the parentheses or the composition. That's not a bad guess. Let's see what happens. So I'm going to say, let's let u be equal to pi minus pi x cubed. If we take our derivative of this, well, the derivative of the pi is 0. The derivative of opposite pi x cubed is going to end up being negative pi times 3x squared dx. Now, there's some good news and there's some bad news about this. The good news is that if you look back at the original integrand, let's try to piece together things that we have from the derivative. Okay? Now, we already know that this x, or pi minus pi x cubed, is our u. Dx is part of the du. Also, pi x squared is part of the du. What you'll notice is that the only thing that we don't have is the negative 3. So couldn't we just, to get rid of the negative 3, divide both sides by negative 3, and then we can substitute? So it looks like that perhaps a good substitution is going to be the opposite of du over 3 to be equal to pi x squared dx. So now we can go ahead and substitute. So by substitution, anything that I double underline is going to become part of negative du over 3. And then obviously, whatever's inside the parentheses, that's what we made equal to the substitution. So I believe that we could say that this is going to be sine of u times negative du over 3. And the only reason I used parentheses was because of the negative sign there. All right. Just like the previous problems, let's go ahead and factor out the negative 1/3 before we do any integration. So I'm going to factor out a negative 1/3, and now we're left with the integral of sine u du. I want you to notice that in all three of the problems that we're working, sine u du is a basic integral, and that's what we're trying to get down to. Sine u du, sine u du, sine u du. So you always want to get down to something that's a basic integral after you're done the substitution. By now we should know the antiderivative of sine is negative cosine. So I'm going to say this is negative 1/3 times negative cos of u plus c. And then if I was to clean this up and make it into a nice answer, notice that we have a double negative here, so it ends up being a positive. I can move the cosine to the numerator, and then I can back substitute for the u. So I believe one form of the answer, not saying it's the only form, but probably like the classic version of this, would be that we have a cosine of the original u, which was pi minus pi x cubed. We're going to divide that by 3, and we're going to add our plus c. Again, if you want to check this, then what you would do is you would go ahead and find the derivative of that. Okay? Although that might be a little bit difficult, so we might want to abstain from that and just trust our instincts on this. So hopefully this is helpful to kind of get an idea of 3 problems that are similar as to how to attack going through and being able to find the antiderivative using a U-substitution, and some of the algebraic and calculus techniques to be able to do that with respect to differentiation.